Okay, so today we will be learning about electromagnetic radiation, specifically about black body radiation. But before that, we need to talk a little bit about the temperature. We'll learn much more about temperature in 2 weeks' time. But for today, we need just introduce another unit of measurement of temperature. How we are usually in our everyday life, what temperature scale we are using? Celsius. There is another scale which used in physics, it's Kelvin. It's called absolute temperature. Why is this temperature called absolute? The thing is the temperature, again, we will learn in 2 weeks' time, approximately. The temperature related to the motion of the molecules in the body. The faster they move in, the higher the temperature. More detail later on. So, when we're cooling any body, we're cooling it down, the motion of the molecules in it becomes slower, 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 and slower. And eventually, it stops completely. And that's called absolute zero. When there's no motion of the atoms or molecules happens. They're not moving. And that's called absolute zero of the temperature. So in the Kelvin scale, there could not be negative temperatures. There cannot be negative motion. And that zero in Kelvin equal negative 273.15 degrees Celsius. We pretty much will be using 273 in our calculations. So 0 degrees Celsius equal 273 degrees Kelvin. And the size of the 1 degree is the same of Celsius and Kelvin scales. So if, let's say, temperature changed from 0 degrees Celsius to 20 degrees Celsius, the temperature in Kelvin changed from 273 Kelvin to 293 Kelvin. So difference in the temperature will be same. Yes?
What happens when there's a temperature below negative 273 Celsius?
It cannot be.
Is that the lowest?
It is the lowest possible temperature in the nature, because at that temperature, all motion of molecules stops. They're not moving anymore. So that's the lowest possible temperature. So we will be using in our calculations, we will be using the temperature in kelvins. So I just introduced, we will learn more about that in approximately 1.5 weeks. Now, I mentioned that we will look today into the black body radiation. Title is electromagnetic radiation. Electromagnetic radiation. And I'm saying, looking into the black body radiation. What is black body? Any object which has temperature emit electromagnetic waves, but they emit it a bit differently. So, if we will look into the graph, this is a wavelength in micrometers, 10⁻⁶ meters, and this is how much energy is emitted. And there are curves built for few different temperatures. And that's it for black body. Black body is the object which absorbs all radiation that falls on it. All 100% does not reflect any of it. That's called black body, which absorb 100% of radiation. And so when this object, black object, is heated up, it emits the most radiation compared to any other object which can reflect. So, as you can see, this is a curve at 3000 Kelvin, this at 4000, 5000, and so on. As you can see, each object emits electromagnetic radiation in the wide spectrum of the waves, of the wavelengths. But the maximum is different. The shorter wavelengths, the higher the temperature, first, more radiation is emitted, because how much radiation is emitted is pretty much area under the curve, which is beyond the school curriculum. So, but as you can see, at 4000 Kelvin, we have much more area under the graph compared to 3000, so much more radiation emitted. Also, at what wavelengths we have the maximum of radiation? The higher the temperature, as you can see, at 3000, the maximum radiation happens at about probably 0.75 micrometers. At 4000, it turns into this is a region where visible light is. At 4000, it becomes about 0.67. At 5000, it becomes in about 0.5 micrometers. So the higher the temperature, the shorter is wavelength at which maximum of radiation is emitted. And we will be doing calculations with it, because there is a law. There is a law called Ven's law. Ven's law connecting temperature and the peak wavelengths. And it is that maximum wavelengths, it's not maximum wavelengths, it's wavelengths at which the maximum radiation is emitted, equal, the constant is 2.898 times 10 in negative 3 divided by temperature in kelvins. This is called Ven's law. So as higher the temperature, the shorter will be wavelengths at which maximum radiation happens. For example, let's find what is the usual temperature of the human body. Yeah, between 36, 37. Let's take 37 degrees Celsius. And let's convert it into the Kelvin. Need to convert it into the Kelvin. 37 plus 273.
310.
310 Kelvin. So let's calculate at what is the maximum, at which wavelengths our body emits the maximum of the radiation. We have maximum wavelengths of maximum radiation will be equal to 2.898 times 10 negative 3 divided by 310, and that will be approximately yeah, you calculated?
0.0000935.
So 9.35 will be times 10 in negative 5 meters. Or in nanometers, that will be 9.35 times What it will be
10
times
to the
what?
negative
Isn't
x.
it 10?
Nano 10 negative 9.
Negative 6.
So it needs to be 10 in the power of 4. So 9,350 nanometers. If you look on your electromagnetic spectrum in your booklet, what type of radiation is this with this wavelength? What type of radiation? Look on the spectrum. Look on the spectrum that you have in your booklet. What type? We learn about 7 types of radiation. The radio, infrared, visible, and so on.
Infrared.
This is infrared.
Isn't it 93 to the 5.9?
Ah, sorry, 99. It is. Yeah, moving times 4. Will be 1 more 0. Sorry, 93,500 nanometers. So that is infrared radiation. So our body maximum of radiation emitted by our bodies, and we emit radiation because we have temperature, is in the infrared radiation. Now, let's say some star emit radiation, the maximum radiation emitting is at 7 times 10 negative 7 meters. Maximum of the radiation of certain star is 7 times 10 in the negative 7. Again, what type of radiation it will be? Or 700 nanometers?
Radio waves.
No,
No, visible ultraviolet.
it's visible light. And what will be color of this light?
Red.
Red light. So the maximum is red visible light. Let's find what is the temperature of that star. How we can find the surface temperature of this star? Rearranging this formula, we will get 2.898 times 10 negative 3 divided by 7 times 10 negative 7. That will be equal about approximately 4 times 10 in the power of
4,140.
4,140, well, about 4 times 10 in the power of 3. So 4,000, you say, sorry, 140?
Yeah.
140 Kelvin. So that is the temperature of that star. So surface temperature of the star is that it will be maximum of the radiation it's emitting will be in the red color. Now, what is the color at which, what type of radiation our sun emits the most?
Yellow.
It emits the visible, specifically yellow. Specifically yellow.
Let's go right.
So, is the temperature of the sun higher than this or lower than this?
Higher.
Higher. Temperature has to be higher.
Come on, guys.
We have this yellow light has smaller wavelengths than the red. Smaller wavelengths, higher temperature. So makes sense how Wheeler's law works. It's connecting temperature of the object and at what wavelength the maximum of radiation is happening. And there is another law that relates to the radiation of the object. But this does not tell, this law, Wheeler's law, tell us maximum wavelength. But it does not tell how much radiation object is emitting. And let's think what that will depend. So what if you look on power? What is power?
Watts.
No, it's measured in watts. But what is power?
Current.
What is power? How much energy
Over time.
will be emitted in 1 second. So power, how much energy emitted by the object in 1 second? That is the power. What it will depend on? What do you think?
Resistance.
No, it's not. No electrical current.
Ah.
It will be on temperature, yes. It will depend on temperature. What else? If you will have two objects with the same temperature, one is the size like this, and another is size like this. They have same temperature. Which will emit more radiation? The bigger one, because it's emit from the bigger surface, so it depends on the surface area. Also, to make this complete, so that we can just logically deduce that power of the radiation emitted by the object should be depend on area, surface area, temperature, but exactly that law, it called Stefan Boltzmann's law, is like this. So there are two more. Sigma is a constant, Stefan Boltzmann's constant, and sigma equals, that's a Greek letter sigma, it's equal 5.67. Of course you don't have to memorize it, it will be always given to you on the formula sheet, times 10 in the negative 8 watts per meter squared per Kelvin in negative 4. E is emissivity. E is emissivity, which is a number from 0 to 1. For black body it's 1. For perfect emitter is 1. Now, in the questions, either E will be given to you, emissivity, E emissivity. So it will be, if it's not given to you, you assume that E equals 1. So if in the question you don't have E given to you, that means by default it's we take it equals 1. Now area, you can see the object, spherical objects. Who remember the formula for the surface area of a sphere?
Pi r squared. Pi r d.
4 pi r squared.
4 pi r squared. Thank you. 4 pi r squared. This is the surface area of the spherical of a sphere. So, yes,
What does WM mean?
this is a unit
Yeah.
of the Stefan Boltzmann's
How
constant.
would you say?
W is what? Per meter square per Kelvin in negative 4. What is important, which factor make the most influence on the how much energy is emitted?
Temperature.
Obviously temperature, because it's in the power of 4. And we will learn soon that is actually key, this formula is a key factor to understanding of the climate, of the science of the climate change. It's actually related to this and Ben's law. Yes?
In the P equals, what's the E in O, like what is that?
E,
Yeah.
emissivity.
Yeah. and-
It's described how well object emit radiation. Let's say black body emit 100%, so E equals 1. Other objects emit less. So E is number, E equals number from 0 to 1 inclusive. And in the questions, it, as I say, A, they will be given to you, that of certain object emissivity equals 0.7. If not given to you, always will take it as just 1.
And what about the sigma?
Sigma is the constant, Stefan Boltzmann
So
constant.
sigma is always that.
Yes, it is a constant. It is a constant. So let's calculate. For example, let's calculate, take some star. Let's say radius of a star will take, to make it simple, let's take 1 times 10 in the power of 10 meters. So what will be its surface area? What will be the surface area of the star with such radius? 4 pi times
10 to the power of 20.
10 in the power of 20. So will be equals 4 pi. We can take approximately 1.2 times 10. So times 10 in the power of 21 meters squared. As approximate. Let's calculate, and let's say the temperature of that star. Let's say temperature of that star. Let's say it's not very hot. Let's take 4,000 Kelvin. Let's calculate how much, and we take E equals 1. Let's calculate how much power that star emitted. Power equal 5.67 times 10 negative 8 times area 1.2 times 10 in 21 and times 4,000 in the power of 4. So if we use a calculator,
1.7 times 10 to the power of 28.
0.7 times 10 to the power 28 watts. That's how much energy every second this star will be emitting. Every second.
That's mental.
It's very, very big. And sun emitting even more because temperature of the sun about 1,000 kelvins higher than that. Make sense how we did this calculation? Now I'll give you one more. I'll give you a hard example on application of the Stefan Boltzmann's law. Let's say, can I clean it up? Let's say we have some piece of hot metal which is at the temperature, which has temperature of, let's say, 400 Kelvin. And this piece of metal emit, let's say, 20 watts, sorry, power, it's emitting power of 20 watts. Question is, if we increase, we heat it up more to 500, to 600 Kelvin, that's T1, P1, T2 will be 600 Kelvin. How much power it will be emitting now? How we will find it? Let's write down for P1 equal E sigma A times 400 in the power of 4. P2 equal same E, sigma is constant, same piece of metal, same area, times 600 in the power of 4. How we will solve those simultaneous equations? Yes?
Well, you can sub in that A was 20.
Yeah, we sub in P1 equals 20, yes. How we solve that? How we will find P2? What is the easiest way to find P2?
You do the second equation minus the first 50 Newton.
Don't you times the top one by 6 and the bottom one by 4?
this equation 1, this equation 2, we will divide equation 2, divide by equation 1. Why we will divide? Because almost everything will cancel out. Almost everything will cancel out. We'll have P2 divided by 20 equals E sigma A, E sigma A, have 600 in the power of 4, over 400 in the power of 4, but all of that cancels out. So we have P2 divided by 20 equals 600 over 400 in the power of 4. What is 600 divided by 400?
3 over 2.
It's 3 over 2, yes. So we have P2 will be equal 20 times 3 on 2 in the power of 4, which is 20 times 3 in the power of 4, 81 divided by 16. That simplifies, becomes 5 equal 400, about approximately 100 watts. 405, yeah, approximately 100 watts. Make sense?
No.
Is it 101?
Which step? It's absolutely fine. Which step doesn't make sense?
Most of it.
Okay, we know that some object, some piece of hot metal, at this temperature emits that much radiation. Question is how much radiation, if you will heat it up to this temperature, how much radiation it will emit now. We are writing Stefan Boltzmann's law for the 400 Kelvin. Can I answer one question, then you can answer. And we write it for second temperature. Does that make sense? We want to find P2. We have two equations. And the easiest way, if you divide this equation by this equation. Why is the best way? Because when we divide an equation by equation, left hand side by left hand side, right hand side by right hand side. This is left hand side over left hand side. Why we divide in right hand side? Because all of that cancels out. We don't need to know area, we don't need to know E. And we have just that left. And we just calculate the number. Make sense? Leo, your question.
Oh no, I got 1 over 1.25.
101.
1.25.
Yeah, it's approximately. If you do exactly 100, 1.25. Yes. Yes.
I have a theory. I think I might.
Again, I will just stop recording and we will listen to your theory.
I reckon Raf's gonna revolutionize that. I think we should keep recording.
No.
I think we should keep recording. I think Raf's got.